There is a place, somewhere between sleep and waking, where the mind loosens its grip on the day, where the lists and the worries and the little urgencies of ordinary life begin to soften at the edges, like ice left out on a counter, quietly, gradually, without any effort at all. That is the place we are heading tonight, and tonight we are going to travel farther than you might expect, not across a continent, not even across the earth. Tonight, we are going to drift outward, past the moon, past the planets, past everything we have ever sent into the sky, all the way to the very edge of the solar system, and then just a little beyond. We are going to follow two small machines that have been traveling through the dark for nearly 50 years, and we are going to discover, together, what they found when they finally reached the boundary where our sun's light and warmth and wind give way to something older, vaster, and stranger than anything our models ever predicted. So, if you are lying down, let your body settle a little more deeply into the surface beneath you. Feel the weight of your arms, your legs, the gentle pressure of the pillow behind your head. There is nowhere you need to be, nothing you need to do. For a little while tonight, the only journey that matters is this one, and it requires nothing from you but the soft, easy willingness to listen. If you find this kind of exploration restful and wonderful, you might take just a small moment before you drift too deeply to like this video or subscribe to the channel. It is a simple thing, a single tap, and it helps these stories find their way to other curious minds who are lying in the dark just like you, looking for something vast and gentle to carry them towards sleep. There is no pressure and no urgency, but if it feels natural, do it now, while you are still just awake enough to remember. Now, let us begin at the beginning, which is, in its own quiet way, also a kind of ending. The year is 1977. Think about what that means for a moment. The world is different. There are no smartphones, no internet, no personal computers sitting on kitchen tables. The most powerful computers on Earth take up entire rooms and require teams of specialists just to keep them running. And yet, that summer and that early autumn, engineers and scientists at NASA are doing something that will turn out to be one of the most remarkable things our species has ever accomplished. They are building two spacecraft and preparing to send them outward into the solar system on what everyone expects to be a 5-year mission. Nothing more ambitious than that. 5 years. Study Jupiter and Saturn. Then drift quietly into the outer dark as the power fades and the instruments go silent. A finite, bounded thing, like so many of our plans. Voyager 2 lifts off on August 20th from Cape Canaveral. Voyager 1 follows on September 5th, taking a faster trajectory so that it will arrive first at Jupiter and Saturn despite having launched second. That is why the names seem backward if you think about them too hard. Voyager 1 did not launch first. It arrived first. Names have a way of telling only part of the story. Each of these spacecraft weighs a little under 2,000 pounds. They stand about 12 feet tall. They are, by almost any modern measure, almost absurdly limited in what they can do. The computers aboard each one carry about 68 kilobytes of memory. Your phone, the one that might be sitting on the nightstand beside you right now, has millions of times more memory than both Voyagers combined. And yet, these machines, these modest, humble, limited machines, are still out there, still moving, still sending back faint whispers of signal across billions of miles of absolute nothing, nearly 50 years after they left the ground. The mission was called the Grand Tour, and the name captures something real about the opportunity that NASA was seizing. Once every 176 years, the outer planets of the solar system align themselves in just the right configuration to make a kind of cosmic shortcut possible. When the planets are arranged this way, a spacecraft can use each one's gravity as a kind of slingshot, borrowing a little of each planet's momentum to accelerate toward the next. Without this alignment, visiting all 4 outer giants, Jupiter, Saturn, Uranus, and Neptune, in a single mission would require more fuel than any rocket could possibly carry. But with it, 1 spacecraft could do what otherwise might have taken a dozen. That alignment happened to be available in 1977. NASA took the window, And the two Voyagers were born of that opportunity. The planets arranged themselves. The engineers built the machines. The rockets fired. And then there was nothing to do but wait and watch and listen. Now, to understand what Voyager eventually discovered at the edge of the solar system, it helps to understand what scientists thought was out there before Voyager arrived. Think of it this way. Imagine you are holding a garden hose and you are standing in a room full of water. The hose is spraying outward in all directions from a nozzle at the center, and the water flowing from it has to go somewhere. Eventually, the pressure from your hose meets the pressure of the water already in the room, and a kind of boundary forms, a place where your water stops pushing and the room's water starts pushing back. That boundary exists because two pressures are in balance. The solar system has something very much like this, only instead of water, the substance in question is plasma, a kind of superheated soup of charged particles that the sun breathes out continuously in all directions. This constant outward breath from the sun is called the solar wind. Scientists discovered it in the late 1950s and early 1960s. A physicist named Eugene Parker, working at the University of Chicago, had actually predicted it would exist before anyone had confirmed it. He showed mathematically that the outermost layer of the sun's atmosphere is so extraordinarily hot that it cannot stay bound to the sun by gravity. It has to flow outward. His prediction was controversial at first. Some colleagues believed the solar wind must be an occasional thing, present only during solar storms, not a constant stream. But spacecraft measurements in the early 1960s settled the question. The solar wind blows every day, every hour, every second, regardless of whether the sun is quiet or stormy. About 1 million tons of material per second streams outward from the sun in all directions, moving at somewhere between 250 and 500 miles per second. That is fast, very fast. But the sun is so enormous, so impossibly massive, that even losing 1 million tons per second, it would take trillions of years to lose any significant fraction of its total weight. This wind flows outward for a very long time before it meets anything that can slow it down. Consider that the distance from the Earth to the Sun is about 93 million miles. Scientists use that distance as a unit of measurement, 1 astronomical unit, or AU, to make the larger distances of the solar system a little easier to think about. Neptune, the farthest planet, orbits at about 30 AU, 30 times the Earth-Sun distance. And even beyond Neptune, the solar wind keeps flowing. It does not care about the planets. It does not stop for them. It streams past them and keeps going, out, into a region where there are no planets, no moons, no spacecraft except for Voyager. Nothing but the wind itself and the vast, cold emptiness of the outer solar system. But eventually, even the solar wind has to meet its match, because the space between the stars is not completely empty. Between the stars, there is a thin, barely there scattering of gas and particles called the interstellar medium. The word medium here means something like material or substance. It is extremely tenuous. If you could take a cubic centimeter of air from the room you are lying in right now, you would find roughly 10 to the 19th power particles inside it. That is a 1 followed by 19 zeros. The interstellar medium, by comparison, contains something like 1/10 of a particle per cubic centimeter, which is to say, it is almost nothing. It is a better vacuum than anything any laboratory on Earth has ever managed to create. And yet, it is not nothing. Over enormous distances, even this near emptiness has mass, pressure, and momentum, and it pushes back against the solar wind. Where these two pressures finally balance, the outward push of the solar wind against the inward push of the interstellar medium, a boundary forms. Scientists gave this boundary a name. They called it the heliopause. The helios part comes from helios, the ancient Greek name for the sun. The pause part simply means stopping, or boundary. The heliopause is where the sun stops. It is the edge of the sun's dominion, the outermost frontier of the bubble of influence that our star has carved out for itself in the interstellar medium. Beyond the heliopause, the space is no longer shaped by the sun. The magnetic field out there does not come from our star. The particles drifting through that space did not originate in our solar system. The rules that govern that region of space are set by the galaxy as a whole, not by the small yellow star at the center of our small cosmic neighborhood. It is, in a very real and profound sense, another universe from the one we were born into, even though it is right next door. By the 1980s and 1990s, scientists had built sophisticated computer models to predict exactly where this boundary would be. They used something called magnetohydrodynamics, which sounds very technical, but the idea is simpler than the name suggests. It is simply the science of how magnetic fields and flowing plasma interact with each other, like a kind of fluid dynamics that has to account for the additional complexity of magnetic forces. They ran three-dimensional simulations. They factored in the solar wind pressure. They estimated the density and pressure of the interstellar medium from astronomical observations. They accounted for the fact that the Sun is not stationary but is itself moving through the galaxy, orbiting the galactic center at a speed of about 137 miles per second, which works out to something close to 500,000 miles per hour. Their conclusion, after all this careful work, was that the heliopause should be located at roughly 90 to 100 astronomical units from the Sun. That is about 8 to 9 billion miles. It seemed like a reasonable estimate. The physics was solid. The data they had was the best available. They drew their diagrams, wrote their papers, updated their textbooks, and waited for the Voyagers to confirm what they had predicted. They were wrong. Not slightly wrong, not wrong in the way that first estimates are often a little off before being refined. They were wrong by billions of miles. Wrong about the shape, wrong about the structure of the boundary itself, wrong about what lay on the other side. And the way they were wrong turned out to be far more interesting and far more beautiful than being right ever could have been. But before we follow the Voyagers all the way to that boundary, it is worth pausing to appreciate something. Think again about those 68 kilobytes of computer memory. Think about the fact that these spacecraft were designed using slide rules. Think about the fact that the signal they send back to Earth is about 23 watts of radio power, which is less than most light bulbs use, and that by the time that signal crosses the billions of miles between Voyager and us, it arrives at Earth as 1/quintillionth of a watt. 1/quintillionth. A number so small it barely seems like anything at all. And yet we detect it. We decode it. We find the science hiding inside it. The transmitters are weaker than a nightlight. The computers have less memory than a digital watch. The entire engineering philosophy of the Voyagers was built on simplicity and redundancy, because the engineers knew these machines would be operating far beyond any possibility of repair, in an environment colder than almost anywhere on Earth, bombarded by radiation, running on a power supply that diminishes a little more with every passing year. Power comes from devices called radioisotope thermoelectric generators, or RTGs, 3 per spacecraft. Inside each one is a quantity of plutonium-238, which decays naturally over time, and in doing so releases heat. Thermocouples, which are simple devices with no moving parts, convert some of that heat into electricity. At launch, each spacecraft generated about 470 watts. By now, that number has fallen to roughly 250. Engineers must decide every few months which instrument to power down, which heater to turn off, how to keep the most critical systems alive on a shrinking energy budget. It is like managing a candle that slowly burns itself down. The flame is still there, but there is less of it every year. In 2020, NASA turned off the heater for one of Voyager 2's instruments to save power. The instrument dropped to temperatures far below its design specifications. The engineers expected it to fail. It did not. It kept working, decades below the temperature it was ever supposed to endure, because the people who built these machines in the early 1970s built them with a kind of loving, careful thoroughness that has outlasted every expectation. Consider what it takes to talk to these spacecraft now. There's a network of enormous radio antennas called the Deep Space Network, with facilities in California, Spain, and Australia. spaced around the Earth so that at least one dish is always pointed toward the outer solar system. Each antenna is 230 feet across. When Voyager 1 sends a signal, it takes over 22 hours to reach Earth. When engineers send a command back, they wait another 22 hours to know if it arrived. A simple exchange, a question, and an answer takes more than 44 hours. You could fly to the other side of the world and come back twice in the time it takes for a single command to reach Voyager 1 and a reply to return. Imagine debugging software written 50 years ago, running on hardware no one can touch, where every attempt at a fix takes nearly 2 days just to confirm whether it worked. And yet, they do it. In 2002, engineers uploaded new code to Voyager 1 to work around a failing memory module. In 2013, they switched Voyager 2 to backup thrusters that had not been used in 37 years. The thrusters fired perfectly. 37 years of dormancy in the cold dark between the planets, and they still worked. Some things, if they are built with enough care, simply endure. This is the technology that discovered what lies at the edge of the solar system, not the sleek, modern instruments of some future era. These humble, patient, ancient machines with their vanishing power and their 22-hour signal delays. Keep that in mind as we follow them outward, because what they found was extraordinary, and it was found with tools that, by modern standards, barely work at all. Voyager 1's first encounter with the outer solar system's boundary region came in December of 2004. The spacecraft was at 94 astronomical units from the Sun, over 8 billion miles. Scientists had predicted the first significant boundary, called the termination shock, would be encountered somewhere around 75 to 90 AU. Voyager was already past that range. Already the models were beginning to show their cracks. The termination shock is not the edge of the solar system itself. Think of it as the first warning sign that the edge is near. It is the place where the solar wind, which has been flowing outward at supersonic speeds, suddenly slows down. Supersonic here means something specific. Sound, in a plasma like the solar wind, travels at a certain speed determined by the temperature and composition of the plasma. The solar wind is flowing considerably faster than that, 5 to 10 times faster. When supersonic flow meets resistance, a shock wave forms, the same way a supersonic airplane creates a sonic boom in the air ahead of it. At the termination shock, the solar wind suddenly slows from those supersonic speeds down to something much more modest. The plasma heats up, it compresses, the magnetic field becomes more tangled and energetic, and particles get accelerated to surprisingly high energies by the electromagnetic forces associated with the shock itself. But even before Voyager reached the termination shock, something odd was happening. The boundary was not staying still. In 2002, Voyager detected signs of the shock at 85 AU, and then the shock moved, pushed outward by a surge in the solar wind. Voyager found itself back in the supersonic solar wind. The signatures of the shock disappeared. Then, in 2003, they returned. The shock washed over the spacecraft and then retreated again. Finally, in December of 2004, Voyager crossed and stayed in the slower, denser plasma on the other side. This breathing motion of the boundary was the first hint of something that would turn out to be a central theme of the entire heliopause story. The edge of the solar system is not a fixed line. It is not a wall you can draw on a map and know with certainty that here the solar system ends. It moves. It breathes. It responds to the sun's activity, to storms and surges and quieter periods, pushing outward and pulling inward like something alive, like the slow tidal movement of something immeasurably vast. Even as you lie there in the dark, that boundary is moving. Right now, tonight, it is somewhere between 100 and 130 astronomical units from the sun, give or take, shifting in response to conditions we cannot fully predict. The edge of the world you live in is not fixed. It undulates with the breath of the star that made you. That is a thought worth carrying quietly into sleep. But we are only beginning. The termination shock was just the first discovery. Beyond it lay the helios sheath, and beyond that, the heliopause itself, and beyond that, something none of the models had. Predicted, something that took over a year of scientific debate to even agree on how to name. We will get there. Take a slow breath. Let the darkness settle around you. We are still traveling, still moving outward, still following these two small patient machines through the dark. After crossing the termination shock, both voyagers entered the region called the helios sheath. It is worth sitting with that word for a moment, the way you might turn a smooth stone over in your hand. Helios sheath. The sheath is the part of a scabbard that holds a sword, the protective layer between the blade and the world outside. And that is not a bad way to think about this region. It is a kind of buffer, a transitional space, a thick layer of slowed and heated solar wind plasma that sits between the inner solar system and true interstellar space. Scientists had expected it. They had modeled it. They thought it would be roughly 10 to 20 astronomical units thick, maybe a bit turbulent, but fundamentally predictable. A transition zone with a clear beginning and a clear end. The reality turned out to be considerably more strange. After crossing the termination shock, Voyager 1 began moving through the helios sheath. The plasma around it was denser than in the solar wind region, hotter, more turbulent. Magnetic field lines were tangled and irregular. The spacecraft was still clearly inside the Sun's domain. The particles around it had originated from our star, and scientists expected that after perhaps 5 to 10 years of travel through this region, Voyager would reach the heliopause itself, based on where the termination shock had been, and based on their models of the helios sheath's thickness, they estimated the heliopause crossing might happen around 2015, at roughly 100 to 110 AU from the Sun. Reasonable, consistent with the physics. A prediction made in good faith by careful scientists. Then, starting around 2010, something began to change. Voyager 1 started, detecting increasing levels of what are called galactic cosmic rays. These are high-energy particles, mostly protons, that have been flung across the galaxy at tremendous speeds by violent events, supernova explosions, pulsar winds, collisions between enormous clouds of gas and magnetic field structures. They are, in a sense, the galaxy's background noise, the constant gentle rain of energetic particles that flows through interstellar space at all times. In the inner solar system, the Sun's magnetic field and the outward pressure of the solar wind act like an umbrella, deflecting and reducing these cosmic rays before they can reach the planets. The deeper into the heliosphere you go, the weaker that umbrella becomes, and the more cosmic rays get through. So some increase in cosmic ray intensity as Voyager moved outward was expected, but the increase that began in 2010 was larger than expected. More concerning, at the same time, lower energy particles that had originated from the Sun were decreasing. Those solar particles should not have faded until Voyager actually crossed the heliopause. They were fading early. Something was happening that the models had not predicted. For 2 years, scientists watched this gradual change with a mixture of fascination and puzzlement. Voyager was still clearly in the helios sheath. The instruments still detected the signature of solar plasma. The magnetic field still behaved like the Sun's field. And yet the balance between galactic and solar particles was shifting in ways that were hard to explain. Then, in June of 2012, Voyager 1 detected something completely new. Something that required scientists to come up with a name they had not needed before. The magnetic field in Voyager's immediate vicinity suddenly became remarkably organized. Instead of the tangled, turbulent field of the helios sheath, the field lines straightened out and pointed radially outward from the Sun, like spokes on a bicycle wheel, orderly and clean. And particles were flowing along these field lines in both directions simultaneously. Solar particles moved outward along them. Galactic cosmic rays flowed inward. The field lines were acting like open channels between the two regions, like a highway connecting the helios sheath directly to interstellar space even though the heliopause itself had not yet been crossed. Scientists called it the magnetic highway, and the name captures something real about what they were seeing. On a highway, traffic. moves in both directions. Vehicles go and come. The road does not belong to one side or the other, it simply connects them. These magnetic field lines were doing exactly that, threading through some kind of structural feature of the boundary region that allowed particles from both sides to travel freely along them. No model had predicted this, no simulation had produced anything like it. The magnetic highway was a discovery that had not been anticipated, which is one of the most interesting kinds of discovery there is. The kind that tells you there is something happening that your current understanding simply has no framework for. The kind that forces you to look at the universe a little differently than you did before. Have you ever thought about how strange it is that something can exist for billions of years before anyone notices it? The magnetic highway had been there all along, presumably, or at least something very much like it had been operating at the boundary of the heliosphere long before Voyager arrived. But it took a small machine the size of a large satellite dish, built 50 years ago, traveling for decades at 38,000 miles per hour, to finally drift through that region and notice it. The universe is full of things that have never been seen by any eye, and the ones we do eventually find have a way of changing everything. Voyager 1 spent roughly 2 months traveling through the magnetic highway. During this time, cosmic ray intensity was higher than anywhere else in the Helios heath. Solar particle intensity was lower. The spacecraft was moving through a region that had direct access to interstellar space, a kind of anteroom, a threshold, a neither here nor there space that belonged to both worlds at once. And then, on August 25, 2012, everything changed. The change happened over the course of a few days, which in astronomical terms is almost instantaneous. Solar wind particles essentially vanished. Galactic cosmic rays jumped up to a new, higher, steady level. The instruments recorded numbers that, taken together, pointed strongly toward one conclusion. Voyager had crossed the heliopause. It was in interstellar space, but there was a problem. The magnetic field did not rotate. Scientists had expected that crossing the heliopause would involve a measurable change in the direction of the magnetic field. The Sun's field and the galaxy's field were presumed to be oriented differently, and crossing from one to the other should produce a detectable shift. But Voyager's magnetometer showed nothing of the sort. The field was pointing in essentially the same direction after the crossing as it had been before, which meant that either Voyager had not actually crossed the heliopause, or the galactic magnetic field in that particular location happened to be aligned with the Sun's field. Through some coincidence or something else entirely was going on that the models had not accounted for. What followed was more than a year of scientific debate. Meetings, papers, counterpapers, careful reanalysis of the data. Some researchers were confident the crossing had occurred. The particle data was unambiguous. Solar particles had vanished. Galactic cosmic rays had surged. The numbers looked like interstellar space. Others argued that without a magnetic field rotation, the crossing could not be confirmed. Maybe Voyager was in some intermediate region, a kind of no man's land between the heliosheath and true interstellar space. Maybe the heliopause had layers that the models had not anticipated. Maybe the magnetic highway had deposited Voyager somewhere strange and unprecedented that had no name yet. This kind of debate is one of the most honest things science does. The data was real, the interpretations were multiple, and the scientists involved were not arguing about politics or preference or whose theory they happened to like best. They were arguing about what the universe was actually doing, and they were taking the question seriously enough to fight over it carefully and methodically until they found an answer they could all accept. Finally, in September of 2013, more than a year after the crossing, NASA officially announced that Voyager 1 had entered interstellar space on August 25, 2012. The magnetic field confusion was eventually resolved by a simple, somewhat astonishing explanation. The local galactic magnetic field, in the specific region of space where Voyager 1 crossed the heliopause, just happened to be oriented nearly parallel to the Sun's field. Not because of any deep physical reason, not because of any structural connection between them, but as a matter of pure cosmic coincidence. The galaxy's field in that neighborhood pointed the same way as the Sun's field at that particular location. Two vast, independent magnetic structures, separated by a boundary billions of miles wide, happened to be aligned there. The universe, it turns out, does not always announce its most important moments with dramatic fanfare. Sometimes you cross the greatest threshold your species has ever crossed and the instruments barely flinch. Think about what that means. Just for a moment. Consider for a moment that you could travel for 35 years, cross a boundary no human-made object had ever crossed before, and the most sensitive magnetic sensor ever flown on an interstellar spacecraft would report only that things looked more or less the same on the other side. Not because the crossing was unimportant, not because the two regions are actually the same, but because the universe arranged its local details in just such a way that the most expected sign of the transition happened to be absent. How many moments in our lives are like that? How often do we cross some invisible line, move from one state of things to another, and only recognize afterward, sometimes much later, that the crossing has occurred? Voyager 1 was confirmed at 121 astronomical units from the Sun. That is 11.25 billion miles. Scientists had predicted the heliopause would be at 90 to 100 AU. It was 30% farther out than the model's forecast, 2.5 billion miles beyond where the diagrams had placed it. The heliosphere was simply larger than anyone had expected. The most likely explanation, worked out in the years following Voyager's crossing, is that the local interstellar medium is less dense than the models had assumed. The pressure pushing inward on the heliosphere is a little lower than estimated, so the solar wind expands a little farther before it meets enough resistance to stop. A small difference in density, multiplied across billions of miles, becomes a very large difference in location. This matters in ways that extend beyond simple curiosity. The heliosphere is a shield. It is the structure that stands between the inner solar system and the full, unattenuated intensity of the galaxy's cosmic radiation. A larger heliosphere means more shielding. It means the cosmic ray environment inside, in the region where Earth orbits, is somewhat gentler than it would otherwise be. Over geological timescales, changes in the heliosphere's size and structure could affect the amount of cosmic radiation reaching Earth's surface, which in turn could influence atmospheric chemistry, the formation of certain isotopes, possibly even cloud formation and climate. The Voyager discoveries are not merely a story about two spacecraft. They are a story about the conditions that made life on Earth possible, and about how those conditions could change. Voyager 2's crossing came later, on November 5, 2018, at 119 AU, 6 years after Voyager 1. The two spacecraft crossed at nearly the same distance from the Sun, which is itself interesting and informative. Recall that they crossed the termination shock at different distances, Voyager 1 at 94 AU and Voyager 2 at 84, a difference of 10 AU, nearly a billion miles. That asymmetry had suggested the heliosphere was not a simple symmetric sphere, but the heliopause crossings were much closer in distance. What does that tell us? It tells us that the heliosphere's shape is complicated. It is not a sphere, but it is also not as dramatically lopsided as some early models suggested. The asymmetry is real but subtle. The nose of the heliosphere, the direction the Sun is moving through the galaxy, is compressed. Slightly. The sides are roughly where the models expected. The tail, stretching out behind the Sun's direction of travel, may extend for hundreds of AU, but we have not measured it directly. The Voyagers are not traveling in that direction. They are heading out from the nose and the side, and they have given us snapshots of those two regions. The rest remains to be explored. Think of it like trying to understand the shape of a cloud by standing in two different places and noting where your hand disappears into the mist. You can learn something, but you cannot map the whole cloud from two data points. You know it has a boundary. You know roughly where that boundary is from where you are standing, but the full three-dimensional form remains uncertain. Voyager 2's crossing was different from Voyager 1's in another meaningful way. It happened faster. Where Voyager 1's transition had taken years, involving the magnetic highway and gradual changes in particle populations, Voyager 2's crossing took roughly 1 day. A sharp, clean transition. And unlike Voyager 1, Voyager 2 detected a clear rotation in the magnetic field, about 20 degrees. Not a dramatic flip, but measurable and real. The two spacecraft crossed the same boundary at nearly the same distance and yet experienced very different transitions, which means the heliopause is not uniform. Its structure, its thickness, its magnetic geometry, all of these vary from one location to another, shaped by local conditions, in ways that a simple model cannot capture. After both spacecraft crossed the heliopause, another surprise was waiting in the data, a surprise that no one had predicted, and that turned out to reveal something profound about the Sun's reach. When the Sun produces a powerful outburst, a coronal mass ejection, a strong surge in the solar wind, that pulse of energy travels outward through the heliosphere. It moves at supersonic speed, pressing outward against the slower plasma ahead of it. When it reaches the heliopause, it hits like a hammer blow against the boundary, and that impact sends a wave outward into the interstellar medium itself, a shock wave traveling through the thin plasma beyond the heliopause, moving at the speed of sound in that medium, which is much slower than the solar wind, about 60 miles per second, but fast enough to cross several AU in a year. Scientists called these waves tsunami waves. The name is vivid and appropriate. A tsunami begins far from shore, set in motion by a distant event, an earthquake, a landslide, something violent and abrupt. It crosses open water for hours before anyone near the shore has any idea it is coming, and when it arrives with force accumulated over all that distance. The solar tsunami waves are like that. An outburst on the Sun, perhaps a year or two before the wave arrives, perhaps even longer, launches a disturbance that crosses the entire heliosphere and then continues propagating into interstellar space. Voyager 1 detected the first of these waves in October and November of 2012, almost immediately after entering interstellar space. The plasma wave instrument recorded oscillations lasting several weeks. Scientists could calculate the electron density of the interstellar medium from the frequency of the oscillations, the way you can estimate the size of a room by listening to how it echoes. A second wave arrived in April and May of 2013, a third in early 2014, a fourth in 2015, each one traceable, back to a specific solar event years earlier, a storm on the Sun that sent its ripples across the entire width of the heliosphere and out into the space between the stars. Have you ever wondered what it would mean for something to have truly long-reach consequences? We tend to think of causes and effects as being close together in time and space. You drop a stone in a pond, and the ripples spread outward and quickly fade. But the Sun's ripples do not fade quickly. They travel across billions of miles. They propagate through interstellar plasma. They arrive years after the event that created them. The Sun is doing something right now, some storm or surge or quiet moment, and the consequences of that action will be felt in the interstellar medium a decade from now. The universe keeps accounts in ways that dwarf our ordinary sense of time. These tsunami detections also helped finally settle the debate about whether Voyager 1 had truly crossed the heliopause. The waves came from the direction of the Sun. They were propagating through interstellar plasma. If Voyager had still been in the heliosheath, still inside the heliosphere, it would have detected direct solar wind pulses, not shock waves propagating through the interstellar medium. The nature of the waves confirmed the nature of the crossing. Voyager was outside. Now pause for just a breath here and consider what the interstellar medium actually is. What Voyager found itself drifting through after crossing the heliopause. We said before that it is almost nothing, that it is better than the best vacuum humans have ever created. And that is true. About 0.08 particles per cubic centimeter, compared to the air you are breathing right now, which contains roughly 10 to the 19th particles per cubic centimeter. The interstellar medium is unimaginably empty. It is so empty that if you took all the interstellar gas in a region the size of a city and compressed it to sea-level air pressure, you would end up with something roughly the size of a sugar cube. And yet Voyager is drifting through this near-nothing and sending back data, temperature measurements, pressure readings, magnetic field strengths. The interstellar medium turns out to be somewhere between 50,000 and 90,000 degrees Fahrenheit. That sounds hot, very hot, and in a technical sense, it is. But temperature, when applied to a gas this thin, means something different from what it means in everyday life. Temperature is a measure of the average speed of particles, the average kinetic energy of motion. In a gas this tenuous, the particles are individually very fast-moving, which is why the temperature reads high. But there are so few of them that if you were floating in interstellar space, you would not feel any heat. You would be surrounded by particles zipping past at tremendous speeds, but so rarely, so infrequently, that you would freeze rather than burn. Not enough particles to transfer their energy to you. Not enough contact. The temperature is high, but the heat is essentially nothing. This is a wonderful kind of strangeness, a place that is simultaneously very hot and very cold, depending on how you ask the question. The interstellar medium is full of paradoxes like this, places where the ordinary intuitions we have built up from living at the bottom of a planetary atmosphere simply do not apply. You have to think differently about it. Let your usual expectations go soft and fluid, like something melting in the dark. The magnetic field measurements also surprised the scientists. Before Voyager crossed the heliopause, models had predicted that the galactic magnetic field should be oriented differently from the Sun's field, angled relative to it in a way that would produce a clear rotation at the boundary. We have already talked about how Voyager 1's crossing showed almost no such rotation, due to a cosmic coincidence of alignment. But Voyager 2's crossing showed a 20-degree rotation. Two crossings, two different measurements, two different pictures of the galactic field in two locations separated by over 100 AU. The field is not uniform. It varies. It has structure. It is shaped by the surrounding galaxy, by plasma currents, by the influence of nearby stars, by magnetic turbulence accumulated over millions of years. This matters because the galactic magnetic field is not merely a curiosity. It is the highway system for cosmic rays. Charged particles, which is what cosmic rays mostly are, cannot travel in straight lines through a magnetic field. They spiral around field lines, following them like trains follow tracks. The orientation and structure of the galactic field determines which directions cosmic rays can flow in, which directions they come from, and how easily they can penetrate into the heliosphere from outside. Understanding the local galactic field is therefore essential for understanding the cosmic ray environment of our solar system. And understanding the cosmic ray environment is essential for understanding, among other things, the long-term radiation history of Earth and the conditions that shaped the evolution of life here. Cosmic rays produce isotopes in Earth's atmosphere. Carbon-14, used in radiocarbon dating, is one. Beryllium-10, recorded in ice cores and ocean sediments, is another. By looking at the abundance of these isotopes in geological records going back millions of years, scientists can reconstruct how the cosmic ray flux has varied over time. Some of that variation comes from changes in Earth's own magnetic field. Some comes from nearby supernova explosions. And some may come from changes in the heliosphere's shielding effectiveness as the Sun moves through different regions of the interstellar medium. The Voyagers, by measuring the conditions at the boundary right now, provide one data point in this long history. A snapshot of the present, placed within a story that extends billions of years into the past. Consider for a moment how strange that is. Two spacecraft launched to study Jupiter and Saturn. Still, decades later, contributing data that affects our understanding of the deep history of life on Earth. Science rarely unfolds in the way we plan it. The most important discoveries tend to arrive from unexpected directions. After crossing the heliopause, both Voyagers also measured the intensity and directionality of galactic cosmic rays with an accuracy that had never been possible before. Inside the heliosphere, the solar wind and the sun's magnetic field constantly scatter and slow down cosmic rays, making it difficult to measure their true unshielded intensity or to determine precisely which directions they come from. Outside, in the interstellar medium, the picture becomes clearer. What scientists found was surprising. Cosmic rays do not come from all directions equally. There is a directional asymmetry, an anisotropy, with higher intensity from some directions and lower intensity from others. This was not unexpected in principle, since the galactic field structure should create such asymmetries. But the specific pattern was not what the models had predicted. More cosmic rays were coming from some directions, fewer from others, and the details did not quite match the simulations. Most counterintuitively, both Voyagers detected lower cosmic ray intensity from the direction of the galactic center than from other directions. The galactic center is the most densely packed region of the Milky Way, with the highest concentration of stars and therefore the highest rate of supernovae, which are the primary accelerators of cosmic rays. You might expect more cosmic rays to be flowing outward from the galactic center toward us, but the measurement showed the opposite. The leading explanation is that the galactic magnetic field is stronger toward the center, and this stronger field traps and scatters the cosmic rays, preventing them from propagating outward efficiently. They get tangled in the complex field structure of the inner galaxy, and fewer reach our neighborhood than simple geometry would suggest. 2 data points do not make a map. The Voyagers have crossed the heliopause in 2 locations and measured the cosmic ray environment in 2 places. The full 3-dimensional structure of the cosmic ray field in our local interstellar neighborhood remains largely unmapped. Future missions will be needed to fill in the picture. But the Voyagers have given us the first direct glimpse, the first measurements made inside the interstellar medium itself rather than from a safe distance behind the solar wind's protective shield. And there is one more thing worth noting here, before we let the story settle into its slower, deeper register. Something that ties all of these discoveries together in a way that says something important, not just about the solar system, but about the nature of knowledge itself. Every major prediction the scientists made about the edge of the solar system was wrong. Not catastrophically wrong. Not wrong in the sense that the entire framework was mistaken. The basic picture, solar wind meets interstellar medium, boundary forms, was correct. The broad outlines were right. But every specific prediction, every quantitative forecast, the distance to the heliopause, the shape of the heliosphere, the sharpness and structure of the crossing, the magnetic field orientation, the properties of the interstellar medium, every single one was off in ways that mattered. The heliopause was 30% farther out than predicted. The shape was asymmetric rather than roughly symmetric. The crossing took years rather than weeks. The magnetic highway was not predicted at all. The interstellar medium's density was lower than estimated. The magnetic field did not rotate the way models expected. The cosmic ray directionality was wrong. 7 major discoveries. 7 ways that reality refused to cooperate with our models. Think about what that means. These were not careless predictions. They were made by talented scientists using the best available data and the most sophisticated computational tools of the era. The equations they used were well established. The physics they applied was real and well tested. And still, reality was more complex, more interesting, more surprising than their best theories could capture. Not because the scientists were inadequate, but because the universe is always deeper than any model, always richer than any simulation, always capable of one more layer, one more unexpected structure, one more thing we did not know we did not know. This is perhaps the most important lesson the Voyagers teach, not the specific numbers, not the exact location of the heliopause or the properties of the interstellar medium. Those are important, of course, and they will inform science for decades. But the deeper lesson is about the nature of exploration itself. We go out to confirm what we think we know. We discover what we actually do not know. And that is always more valuable than confirmation. Lie still for a moment with that thought. The edge of the solar system is billions of miles away. Voyager is out there right now, drifting through the interstellar medium, sending back its faint signal. It does not know that we are grateful for it. It does not know that the data it gathered changed the way we understand the neighborhood our planet lives in. It just keeps moving at 38,000 miles per hour through the dark, and somewhere out there in the interstellar medium, the waves from solar storms are still propagating, ripples from events that happened years ago, crossing the boundary and moving through the plasma, fading slowly as their energy spreads over a larger and larger volume of space. The sun's voice reaching into the dark beyond its own borders, still speaking, even out there. We are going to let the story slow down. Now, let the ideas settle. Let the distances become something you can almost feel, the way you can almost feel the size of the ocean when you stand at the shore in the dark, not quite touching the full enormity of it, but aware, deeply and quietly aware, that it is there. There is something deeply restful about very large numbers when you let yourself stop trying to grasp them and simply float in their vicinity instead. 11 billion miles, 121 astronomical units, nearly 50 years of travel. These are numbers that the mind cannot truly hold, not in the way it holds the distance to the grocery store or the number of steps between the bedroom and the kitchen. They are too large for that kind of knowing. But there is another kind of knowing, softer and more diffuse, that is available to you when you are lying in the dark and the analytical part of your mind begins to loosen its grip. A kind of felt sense of vastness, not understood but somehow experienced. The way you experience the depth of the sky on a clear night without being able to measure it. Let yourself have that now. Let the numbers be large without trying to contain them. 11 billion miles. A signal taking 22 hours just to arrive. 2 small machines, traveling since before many of the people alive today were born. Still out there, still moving, still whispering their findings back to us across a distance that takes light itself most of a day to cross. We have talked about what the Voyagers found at the edge. The heliopause farther than predicted. The heliosphere shaped differently than expected. The transition complex and prolonged and full of surprises like the magnetic highway, the interstellar medium measured directly for the first time, its density and temperature and pressure and magnetic field all slightly different from the models, the tsunami waves propagating outward from solar storms into the space between the stars, the cosmic rays arriving preferentially from unexpected directions. 7 discoveries. 7 ways the universe said, quietly and without drama, that we had more to learn. But there is another layer to this story that we have not yet fully explored. A layer that is less about data and more about meaning. Less about what the instruments measured and more about what the measurements mean for us, for our species, for the question of what we are and where we live, and how we fit into the larger structure of things. It begins with a photograph. On February 14, 1990, Voyager 1 turned its camera backward for the last time. The spacecraft was about 3.5 billion miles from Earth, well past Neptune's orbit, heading outward toward the heliopause that was still decades away. At that point, at the request of the astronomer Carl Sagan, who had been one of the most passionate advocates for including cameras on the Voyager spacecraft, NASA commanded Voyager 1 to rotate its imaging platform and take a series of pictures. A family portrait of the solar system as seen from the outside. 60 frames, covering the inner planets and the sun itself, assembled into a mosaic of our home. In one of those frames, in a scattered band of light created by sunlight refracting through the camera's optics, there's a tiny dot, a pale blue dot, barely a pixel across, suspended in a beam of scattered light like a mote of dust in a sunbeam. That dot is Earth. Every human being who had ever lived at the time that photograph was taken was on that dot. Every war ever fought, every love ever felt, every meal ever eaten, every dream ever dreamed, every moment of kindness and cruelty and ordinary Tuesday afternoon, all of it on that dot. Carl Sagan wrote about what that image meant to him, and his words have carried forward through the decades since, not because they are technically precise, but because they are true in a way that goes deeper than precision. He pointed out that from Voyager's vantage point, Earth had no special significance in the frame. It was simply one small, pale dot among several, smaller than Jupiter, fainter than Venus, indistinguishable from a piece of dust except that we knew it was there because we came from it. All of our importance, all of the weight we assigned to our own history and our own dramas, was invisible from out there. The universe did not arrange itself to highlight us. We were simply present and small and very far from the spacecraft that was looking back. There is something strangely comforting about this when you let it settle in. Not the smallness itself, but what the smallness implies. It implies that the things we worry about, the daily anxieties and frustrations and embarrassments and disappointments, are contained within something much larger. They happen on a dot. They are real and they matter, because we are real and we matter. But they are not the whole story. They are not even a large chapter of the whole story. They are a few sentences, or perhaps just a few words, in a narrative that extends billions of years in every direction. And somehow, knowing that, feeling it, rather than just knowing it intellectually, can make the weight of those smaller things a little easier to carry, or to set down entirely, at least for tonight. The pale blue dot photograph connects to the Voyager discoveries at the heliopause in a way that is worth tracing slowly. The spacecraft that took that photograph went on to travel for another 2 decades and more after the shutter closed. It crossed the termination shock. It entered the heliosheath. It discovered the magnetic highway. It crossed the heliopause. And from out there, from true interstellar space, the entire solar system is not even visible as a dot. It is simply the region of space that the sun's wind happens to fill, a tiny, temporary bubble in the vast, ancient plasma of the interstellar medium, a bubble that the sun has been inflating for the 4.5 billion years of its life, and that will slowly collapse when the sun eventually dies. We live inside that bubble. We have always lived inside it. The bubble is our cosmic home in a more literal sense than most people ever think about. The heliopause is the wall of the house. The solar wind is the atmosphere of the house. The sun is the fire at the center of the house. And beyond the wall, in all directions, the interstellar medium flows past, ancient and cold and vast and largely indifferent, carrying the magnetic field of the galaxy, carrying the cosmic rays accelerated by distant supernova, carrying the ripples of events that happened thousands of light years away and thousands of years ago. The Voyagers left the house. They are the only things we have ever made that have done so. And they sent back a description of what they found on the other side of the wall, and it was stranger and more interesting than we had expected. Consider for a moment what the interstellar medium actually connects. Every star in the Milky Way is embedded in it. The plasma that Voyager 1 is drifting through right now is the same plasma, more or less, that flows past every other star in our galactic neighborhood. The magnetic field lines that Voyager measured connect our local region of space to regions far away, carrying information about plasma flows and particle accelerations across distances of light years. The galaxy, at this very tenuous level, is not a collection of separate stars. It is a connected medium, threaded through with field lines and plasma currents and the echoes of ancient explosions. A web of sorts, loose and thin and almost impossibly sparse, but present. We are connected to all of it. Our sun's magnetic field, at the heliopause, merges in some complicated way with the galactic field. The particles flowing along the magnetic highway travel from inside the heliosphere to outside and back, carrying information between the two regions. The tsunami waves from solar storms propagate into interstellar space and add their small perturbations to the larger structure of the medium. Even from inside our quiet bubble, our sun is participating in the larger conversation of the galaxy, speaking in waves of pressure and magnetic perturbation to a medium that extends across the full 100,000 light-year diameter of the Milky Way. Think about that slowly. The sun is speaking, in pressure waves, in magnetic fluctuations, in the slow outward push of the solar wind. And the galaxy is speaking back, in cosmic rays and magnetic field lines and the density variations of the interstellar medium. This conversation has been going on for 4.5 billion years. We have only just learned to listen to a small part of it. And what we heard, when we finally sent instruments far enough to overhear it directly, was different from what we expected to hear. The Voyager mission was designed for 5 years. It has lasted nearly 50. Every year that it continues is a year that was never planned for, never budgeted for in the original mission design, never anticipated by the engineers who built these spacecraft in the early 1970s. Every year is a gift from careful workmanship, from the decision to use simple and robust systems rather than complex and elegant ones, from the decision to build in redundancy, to use proven components, to accept a little extra weight in exchange for a little extra reliability. The engineers who made those choices are mostly gone now. Some died before Voyager reached Jupiter. Many did not live to see the heliopause crossing, but their choices are still out there, still holding together, still carrying instruments and antennas and golden records through the interstellar medium. The golden records. We should spend a little time with them here, in the slow, contemplative part of the journey, because they are one of the most quietly extraordinary things our species has ever made. Each Voyager carries a golden record, a 12-inch, gold-plated copper disc, physically etched with audio information the way a vinyl record holds music, designed to last for hundreds of millions of years in the vacuum of space. No oxygen, no water, no chemical processes that could corrode or degrade the metal. The information is in the grooves themselves, mechanically encoded, readable in principle with nothing more than a stylus and a way to convert mechanical vibration into sound. The cover of the record carries instructions, etched in, diagrams and binary code explaining how to play it, how to decode the images hidden in the audio signal, and how to find the star the record came from by triangulating against 14 known pulsars. The sounds on the record include things you might hear on almost any night anywhere on Earth: wind moving through trees, rain falling, thunder, waves breaking on a shore, whales singing in deep water, their long, haunting vocalizations traveling for hundreds of miles through the ocean, birds, crickets, a baby crying, laughter, a heartbeat, the sound of footsteps. These are the sounds of a living world. A world where life has been going on for billions of years and has produced, among other things, a species capable of sending these sounds to the stars. The music on the record was chosen by a committee that included Carl Sagan and a group of scientists, musicians, and anthropologists who spent months debating what to include and what to leave out. Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, Stravinsky's Rite of Spring, but also music from Java and Senegal and Peru and Japan and the Aboriginal peoples of Australia and the Pygmy peoples of what is now the Democratic Republic of Congo. Chuck Berry's guitar, Louis Armstrong's trumpet, panpipes echoing across high mountain air, a shakuhachi flute, spare and meditative, music from across the full breadth of human culture and human history. They included greetings in 55 languages, from ancient Akkadian, dead for thousands of years, to modern Mandarin and Spanish and Hindi and English, each greeting brief, each one carrying some version of the same simple message. We are here. We are alive. We hope you are too. There were debates about what to include and what to leave out. Every choice meant something else could not be chosen. How do you represent all of humanity on a single disc? How do you choose which music, which languages, which images? The committee struggled with it. They made compromises. Some cultures were overrepresented and others underrepresented, inevitably, because perfect representation is impossible and a decision had to be made. But the spirit behind the effort was genuine and is worth honoring. These were people trying to say something true about what it means to be human, not just the achievements, not just the beautiful things, but the full texture of life on this particular planet, at this particular moment in the long history of the cosmos. The committee knew, with complete clarity, that the chance of the record ever being found was essentially zero. Space is too large. The Voyagers are too small. They are not aimed at any particular star. They will drift for millions of years without coming close to anything. Even in 40,000 years, when Voyager 1 will pass within 1.5 light years of a star called Gliese 445, it will not enter that star's system. It will drift past, more than 9 trillion miles away from the nearest point of the star's gravitational influence, far too distant to be detected by any civilization that might exist there, even one considerably more technologically advanced than we are today. And yet, the committee made the record anyway, because the making of it was valuable regardless of whether it is ever found. The process of choosing what to put on it required the people involved to ask themselves questions that are worth asking. What do we value? What are we? What would we want another intelligence to know about us? What transcends the specific accidents of our history and culture and speaks to something more universal about minds and lives and the experience of being alive in the universe? These are questions that do not have clean answers, but the asking of them is worthwhile. It is the same kind of worthwhile as looking at the pale blue dot photograph and letting the scale of it wash over you. It does not solve anything. It does not fix any of the real problems that real people face on that small blue dot, but it reorients something. It shifts the frame slightly, and sometimes that shift is exactly what is needed. The Voyagers will eventually fall silent. The plutonium in their RTGs is decaying at 4 watts per year, steadily, inexorably, in the same way that all radioactive material decays, indifferent to our wishes or our needs. By around 2030, perhaps a year or two later at most, the power budget will be exhausted. The transmitters will not have enough energy to send a signal. The last whisper from Voyager will fade into the background noise of the universe, and the deep space network will stop hearing anything from that direction in the sky. But the spacecraft will keep moving. There is no friction in space, no air resistance, nothing to slow them down. They will continue at 38,000 miles per hour essentially forever, or at least for as long as they do not encounter anything that changes their trajectory. In 100 years, they will be farther from the sun than they are today, drifting silently through the interstellar medium they helped us discover. In 1,000 years, still moving. In 10,000 years, still moving. In 40,000 years, Voyager 1 will make its closest approach to Gliese 445, 1.5 light years away, passing in the dark without ceremony, carrying its golden record through a region of space that has almost certainly never been visited by anything made by a living mind. And after that, it will keep going, into the deeper reaches of the galaxy, passing through regions that have never been named because no one has ever been there to name them, moving through plasma that has been undisturbed since long before our sun formed, 5 billion years ago, from a cloud of gas and dust that had itself been drifting since even earlier, since some earlier generation of stars lived and died and scattered their elements outward to seed the next generation. We are made of that material. The carbon in your body was forged in the core of a star that died before the sun was born. The iron in your blood was produced in a supernova explosion so violent it briefly outshone an entire galaxy. The oxygen you are breathing right now was synthesized in stellar cores across billions of years and scattered outward to become part of the interstellar medium, the very medium that Voyager is now drifting through, the very medium that presses against the heliopause, the boundary of the house, where you were born. You are, in a very literal sense, made of the same stuff as the interstellar medium. The atoms in your body have been in interstellar space before. They will be in interstellar space again, long after the sun has died and the Earth has been absorbed into its expanding outer layers and the last traces of our civilization have been ground down by geological processes into something unrecognizable. The atoms will persist. They will drift outward into the interstellar medium and join the slow, ancient circulation of material through the galaxy. This is not a sad thought, even though it might sound like one. It is more like a recognition of belonging. You belong to this larger story, not as a character in it, not as a hero or a protagonist, but as a participant, an expression of it, a temporary arrangement of ancient atoms that has achieved, for a brief and remarkable time, the ability to look outward and wonder about the arrangement. The Voyagers are also an expression of this. They are made of the same ancient atoms, assembled by the same species that assembled the cathedrals and the symphonies and the languages and the greetings in 55 tongues on that golden record. For a brief moment in the long history of the universe, a collection of atoms on a small planet around an ordinary star became curious about the edge of the bubble their star had carved in the interstellar medium and sent 2 small machines to go look. And the machines went, and they looked, and what they found was more interesting than what we expected. The boundary was farther than our models predicted. The shape was more complicated than our simulations suggested. The transition was stranger and richer and more layered than our theories had room for. The interstellar medium was slightly different from our estimates in its density and temperature and magnetic field. The tsunami waves from solar storms reached farther than anyone imagined. The cosmic rays came from unexpected directions. 7 surprises. 7 gifts from reality to our models. 7 reminders that the universe is always one step ahead of our understanding, always holding one more secret in reserve, always capable of producing something that makes us revise the textbooks. Science is not a process that ends. It is a process that deepens. Every answer opens into new questions. Every confirmed prediction rests on assumptions that future instruments will test and find subtly wrong. The heliosphere is larger than we thought, but how does it change over time as the Sun moves through different regions of the interstellar medium? The magnetic highway exists, but how widespread is it, and how does its structure vary around the heliopause? The galactic magnetic field is oriented a certain way near the Voyager crossing points. But how does it vary over larger scales? The tsunami waves propagate into interstellar space, but how far do they travel before dissipating? How do they interact with the structures they encounter? These questions do not have answers yet. They require new missions, new instruments, new decades of patience and work and waiting. NASA is developing a concept called the Interstellar Probe, a spacecraft designed from the beginning for the journey the Voyagers stumbled into by outliving everyone's expectations. The goal is to reach 500 to 1,000 AU within 50 years, traveling at perhaps twice Voyager's speed, carrying better instruments, mapping the heliosphere's shape more systematically, measuring the interstellar medium farther from the heliopause, searching for the bow shock in the interstellar medium that the Sun's motion should be creating, the way a boat creates a wave in water, somewhere around 140 to 200 AU. If the interstellar probe launches in the 2030s as currently hoped, it will not reach its primary science objectives until the 2080s. The scientists who are designing it now will most likely not be alive to see the results. They are doing work whose rewards will belong to people who are children today, or who have not yet been born. This is a particular kind of generosity, one that does not get celebrated enough. The willingness to spend your working life on a question whose answer you will never hear. The willingness to be the person who lays the foundation rather than the person who sees the building completed. The Voyager engineers were like that too, in a way. The spacecraft have lasted nearly 50 years. Some of the engineers who built them lasted barely long enough to see the planetary encounters. The ones who set the trajectory that sent Voyager 2 to Uranus and Neptune in the 1980s had no certainty that the spacecraft would still be functional by the time it arrived. They planned for it anyway. They did the work anyway. And the spacecraft arrived, and Uranus and Neptune were there, and the instruments worked, and the data came back, and the scientists, who were young enough, were still alive to see it. There is something about this that rhymes with the best qualities of human nature. The willingness to invest in things larger than yourself. The willingness to work on time scales that exceed a single life. The willingness to care about questions that will not be answered in your lifetime, because you care about the questions themselves, not just the answers. The Voyager program is a story about that willingness, as much as it is a story about spacecraft and heliopauses and termination shocks and tsunami waves. The Voyagers are dying now, slowly, as they have been dying for decades. Each year, a little less power. Each year, a little colder. Each year, one more instrument going dark, one more heater switched off, one more concession to the shrinking energy budget. The engineers who tend to these spacecraft are doing triage, deciding what can be kept alive and what must be sacrificed. Working with hardware that is 50 years old across, communication delays of 22 hours, debugging software written before they were born. And still they persist. Still, Voyager 1 sends back data from the interstellar medium it discovered. Still, Voyager 2 adds its measurements from a slightly different direction. Still, the Deep Space Network dishes point at their coordinates in the sky and listen for the 23-watt signal that has crossed more than 14 billion miles to arrive as 1 quintillionth of a watt. 1 quintillionth. Write it out as a decimal and you have a 0, a decimal point, and then 17 more zeros before you get to the 1. That is the strength of the signal. That is how faint the voice is, and we still hear it. Let that thought drift through you slowly, like something dissolving in warm water. 1 quintillionth of a watt, 14 billion miles, 22 hours for light to cross the distance. And we built something sensitive enough to listen, and patient enough to wait, and careful enough to decode what it hears. For all our smallness and our brevity and our paleness in the dark, we did that. We sent something out, and we kept listening to it, and what it told us changed what we know about the place we live. The interstellar medium is flowing around Voyager right now. Thin, ancient plasma, threaded with magnetic field lines that connect to the broader structure of the galaxy, carrying cosmic rays from supernova explosions that happened before the sun was born, maintaining a pressure so low that it barely registers by human standards and yet just barely enough to push back against the solar wind and define the boundary of the heliosphere. And Voyager moves through it at 38,000 miles per hour, which sounds fast until you remember that the nearest star is 25 trillion miles away, and at that speed the journey would take 73,000 years. Voyager is not going to the stars. It is drifting in the interstellar medium. It is in the space between the stars, the space that connects them all, the ancient continuous medium that has been here since long before our sun ignited. There is a kind of peace in that image when you let yourself sink into it. Something vast and quiet surrounding a small, faithful machine that is doing its work with the last of its power, sending back its faint reports, telling us what is out there. Not rushing, not complaining, not running out of patience, just moving, steadily and continuously through the dark. The dark is not empty, we have learned. It is full of things that are almost nothing, but not quite nothing. Particles moving at tremendous speeds through a near-perfect vacuum, magnetic field lines connecting star systems across light years, waves from ancient solar storms propagating through the plasma. Cosmic rays carrying the energetic legacy of supernovae that exploded before our planet existed. None of this is visible. None of it could be seen or felt or measured from the surface of the Earth. It took 50 years of patient, faithful travel to get close enough to measure it. And what does it mean that we know this now? What does it mean that the picture we have of the edge of the solar system is more complex and more interesting than it was before? It means that the universe rewards exploration. It means that going out, sending instruments, being willing to travel beyond the comfortable region where our models have been confirmed is worthwhile, not because we will necessarily find what we expect, but precisely because we will not, because reality is richer than our theories, because the universe has more depth than our simulations can represent, because every time we look somewhere new, we find that things are stranger and more wonderful than we had imagined. That is the gift the Voyagers gave us. Not just the specific data, not just the measurements of the heliopause distance, or the interstellar medium density, or the magnetic field orientation. Those are valuable, and will be built on for decades. But the deeper gift is the reminder that we still have so much to learn, that even about our own cosmic backyard, the immediate neighborhood of our own star, We were substantially wrong in ways that mattered, and that being wrong is not a failure. It is the first step toward being less wrong. It is how we learn. You are lying in the dark right now, on a small planet, inside a bubble of solar wind that extends 121 AU in the direction. Voyager 1 traveled, and somewhat different distances in other directions, breathing air that was recycled through living things for billions of years before you arrived, made of atoms forged in stellar cores before the sun was born. The interstellar medium is pressing against the heliopause all around you, at a pressure of roughly 3 quadrillionths of the pressure at your skin right now, maintaining the boundary of the house you were born in. Voyager 1 is somewhere around 100, and 60 AU away, still moving, still listening, still whispering. You are not separate from any of this. You are part of it. You are an arrangement of ancient atoms that became, temporarily and remarkably, conscious and curious and capable of sending machines to the edge of the solar system. That is not a small thing. Even by the measures of the universe, where stars burn for billions of years and galaxies span hundreds of thousands of light years, the emergence of consciousness and curiosity is not ordinary. It may be rare, it may be extraordinary. We do not know, but here it is. Here you are. Let the largeness of it be restful. Let the distances be vast without being frightening. Let the darkness outside be full rather than empty. The magnetic field lines are out there. The plasma waves from ancient solar storms are out there. The golden record is out there, carrying Bach and Chuck Berry and the sound of a heartbeat and greetings in 55 languages, moving through the interstellar medium at 38,000 miles per hour, faithful and silent in the dark. Everything is very quiet out there, very still, in the way that only truly enormous distances can be still. The kind of stillness that is not the absence of things, but the presence of things too vast and too slow to register as movement from any single vantage point. The kind of stillness that feels, if you let it, like rest. Let the solar wind press outward against the interstellar medium, as it has, for 4.5 billion years. Let the heliopause hold its shape, breathing in and out with the slow rhythm of the solar cycle, moving a few AU outward when the sun is active and pulling back when it is quiet. Let the cosmic rays drift through the interstellar medium along the galaxy's magnetic field lines, carrying the energy of supernovae toward our small bubble. Let Voyager move, steadily and unhurried, through the space between the stars. And let yourself be still. Let the weight of the day go soft. Let the edges of your thoughts become less distinct, less urgent, less insistent. There is nothing out there tonight that needs your attention. The heliopause will hold, the solar wind will blow, the golden record will continue its journey through the dark. You are very small, and the universe is very large, and somehow, mysteriously and beautifully, the small thing became aware of the large thing, and sent 2 machines out to touch it. That is enough. That is more than enough. Good night.